Is to look at recent publication on a multi-layer perceptron for obtaining quick parameter estimations of cool exoplanets from geometric albedo spectra. That was a lot. Pretty much it's looking at the albedo spectra of an exoplanet, and it's using a neural net to estimate the parameters of the planet. So the parameters it's looking at are its metallicity, its gravity, its temperature, and various cloud properties. Now I'm looking at the GitHub I have posted for all this with the repository. It has all the results. It has all the raw data. It has the paper you see here. It has a README on how to use the code, and of course the code right there. So I'm going to show a quick rundown of pretty much how to use the code. But before we do that, let's quickly look at this paper, and I suggest you go ahead and look at it if you want more details. The main idea is just to get quick retrievals, because before, if you wanted to estimate properties of a planet, it would take hours, if not days, comparing against multiple models. Now that we created a neural net, it can do it within seconds. If we want to retrain it, it can do it in minutes to hours. It's a lot quicker. So the database we have is taking spectra that look like this. So it has different features on the wavelength, and that gives you different albedo intensities for the y-axis. So there's a lot of dimensions here. We don't talk about that. So we binned them down to reduce the number of dimensions. You'll get here in more detail. This explains how an MLP works, which is a type of neural net. Pretty much you just input a spectrum, learns Latin variables in the hidden layers, and it outputs the different parameters you're trying to regress. Here's all the different techniques we use. They're all in the code. So 80% of the entire data was used to train it. 10% was used to validate, and that's used to test what epoch, when we should stop training, what epoch. And then 10% was a testing set, which was used at the end to corroborate results. It's pretty standard stuff. We added different levels of Gaussian noise. So if you look at table 3 here, there's the raw with no noise added, then 5% Gaussian noise, then 10% Gaussian noise, and 20% Gaussian noise. It's a good way of doing data augmentation and also seeing how your data works with noise. This plot here, figure 6, shows that we use enough training spectra, because as we increase the number of spectra in our training set, the RMSE converges to this low value. So our training set was big enough. So here's some results that compare each of the different parameters. These top left 4 panels are all metallicity. That's that M over H. And then the bottom 4 on the left are gravity. It's log GCM squared. Top right 4 are the temperature. That's TF, effective temperature. And the bottom 4 are FZ. That's the cloud parameter I was talking about. And that's just how thick the atmosphere is. So if you look at these are plotting expected versus estimated. And the black line is a slope of 1, and it shows perfect. If we had a perfect estimator, all of the points would line up on that line. However, you can see it's not the case. Got some variance around the line. So these yellows show test results. Every dot is one test result on one spectrum left out in the testing set. So yellow means it's in one standard deviation of that given parameter's value. So for example, if we look at the very top left figure, the M over H with no noise, we see these purple dots, green dots, blue dots, and yellow dots. So if we look at this 1.0 on the x-axis, again on that top left panel, the yellow dots all fall within one standard deviation of the estimations when the true metallicity value is 1.0. Green is in 2 standard deviations, blue is in with 3, and purple is within 4 or above. So it shows you how the estimations are varied. And you can see how well these line up for each. For most of the cases, the straight line falls into the yellow dots, which is good because that shows that within one standard deviation, most of them are right around where you expect them to be. And you can look at this a little bit more to really interpret this. The main idea is, if you look at these, that the estimations are pretty good. It struggles a little bit the most on the top right. You see the effective temperature on values above 250 Kelvin. It kind of does this like straight horizontal thing. And that's because of model degeneracies, because some spectra at that point, the cloud levels are so negligible that they don't really affect spectra and they all become degenerate. And you can read more about that in the paper if you're interested. Main idea is it doesn't do too bad. And then this shows here at the bottom, it shows a test value right here in black on figure 8 compared to training spectra around it. And you can see this top one, it was predicted pretty well. And that's because all the training spectra with parameters around it look pretty similar to it. You can see the black line falls in between them all. However, in the bottom panel, you can see this is one that struggled a little bit. The test spectrum, not all the training spectra look like it. You know, we have this red and this blue one above it that are pretty different, and even though they have similar parameters to this. So that shows why that one struggled on getting predicted. So that's it about for the paper. We're going to go ahead and look at the code now. I'm not going to go into it too much in detail, but if you want, you can read through this. It's pretty well commented. And I have my email at the top. So if you run into any bugs or questions or anything like that, you can go ahead and shoot me an email. All right, let's look at how to run it. So the very first thing that you want to do is at these very top, I have it set to multi-thread to true and number of threads equal to 4. This is going to be pretty optimal for most computers, but if your computer can't handle multi-threading, or if you're running some issues, you can always just change this to false, and it won't multi-thread. Or you can either decrease the number of threads or increase the number of threads depending on your computer. It's built for thread on CPU, not a graphics card at the moment. I might do graphics later. Right now it's just CPU. All right. So after that, we don't have to do too much. We're just going to run it. It's set so that you can just plug and play. So let's go ahead and I want to find something here first. That's what I'm looking for. So let's go ahead and play. It's compiling. So either you're going to be training or testing. So you want to hit train if you want to train a new network. So say you have different data than what we showed in the paper that you want to train, or you're using different dimensions. You know, maybe you have different wave lengths, or you have different parameters you want to train on. We could train a new network. So I'm going to go ahead and show you how to do that right now. So let's train. And the first thing they're asking for is a path to your training data file. So these are CSV files. And I'll give you an example right now. I'm going to load the test because it's smaller, so it's a little quicker. And there's a format for the CSV files. It's pretty simple. First column is the name of a spectrum. Each row is a different spectrum. Then after the name, you have the different wavelengths. So these are all numerical values. They have to be numerical, and probably should be in ascending order. I don't think that matters too much though. But you see these goes all the way until the end. And at the end, after your last wavelength, you start to have your parameter names. So these have to be non-numerical. And this is set up so that the program can auto-detect your dimensions and your labels. So all you have to do is create a CSV file, and the program should take care of the rest for you, as long as you follow these conventions. Wavelengths for the spectrum, the header has to be numerical, and labels have to be non-numerical. You can have numbers inside these names, but they have to have letters in it. So you can see for this one, I'll plot the top row so you can see exactly what I'm talking about. So this one row is one spectrum. You can see it here. The x-axis is all the wavelengths. These are binned. And the y-axis is the albedo intensity. And it creates this spectrum right here. This one has noise. That's why it's so jagged. All right, and then the last four. For that one spectrum that had a metallicity of 2, a log G of 2.7, a TF of 210, and an FZ of 4. And you can see I have multiple here. I have, yeah, up to 12,000 because a bunch of these are with noise added to it. So that's what your CSV file looks like. So that's what we're reading in here. So we're going to read in 3 CSV files, one for training. And I'll explain what that is in a little bit. So we're going to go and copy this path. We're going to paste it. Then we're going to do one for the validation. Go ahead and copy this path, paste it in here, and now it's asking for one for testing. So we're going to do the final one is testing. And these are big files, so they'll take a couple seconds to load. Yeah, you can access my files. Really quick, so training that's what your network is learning the patterns from. That's what it's fitting on. So that's where it's learning its weights and biases. Validate is used to determine what epoch to use. You know, it's going to train through a given amount of iterations and use the validation set to decide what iteration is the best one. Your test is left out of the entire process, and after you choose a final model, use your test set to see how accurate it is. And it's very important this is left out the entire model, otherwise so that you don't overfit on it. So now we can see it read in the files. So it read in the first file with 102,000 rows, 248 columns, and 4 labels. So you should make sure that this is right. And we have another one for 12,000. And again, these are so much bigger than the original data size because remember we added 10 noisy spectra for each one. So it got a lot bigger. All right, so now it's going to ask how you want to build the MLP. So either you can do auto, and auto will use default values that are set here in the source code. And these values right now, as is from the GitHub, are set to the values used for the MLP with no noise in the paper. So that's using this none up here on table 3. We're trained up to 873 epochs, L1 and L2 and max norm are there. And then if we look at this paragraph right here on the top left, it's with 3 layers, 64, 64, 32, 0.9 learning momentum, cyclic learning, did not use dropout, and it's using ELU activation nodes for hidden nodes, and it's using a sigmoid for the output. So that's the default. You can change these if you want, and then just run auto. And it'll auto detect the number of columns in your CSV file and the number and your labels. And those can be whatever you want. You can also change this to either be right now it's set to regression, so regress is equal to true. If you want it to be classes instead though, if you want it to be one class, you can use class binary. If you want it to be multiple classes, you can use class multi, and then set the threshold required to classify something as a class for class multi. So it doesn't just have to be continuous values. If you want, you can do classes for your spectrum, and it'll learn that just as well. You can also type in own if you want, and the terminal will walk you through all these parameters and pretty much give you a little bit of what each of these parameters are, and then you can enter a value. It's a bit of a long process though, so I think just going straight here to line 2976 and changing these values in the source code is probably a lot quicker. Let's go and do it. So we're going to do auto. So you can see it created an MLP with the parameters set right here that I've highlighted, and it's going to start going epoch by epoch. So right now I have it set to 1,000 epochs. So it's going to train for that many times. And right now I have output. If you scroll down to here, you can see I have different booleans you can set to output different stuff. So if you want more or less output. Right now it's set to be pretty slim, so it's only outputting the needed stuff. Right now I have output results equal to true, and what that's going to do is it's going to output the results after each epoch, the RMSE, for your training and your validation data. And it's also set to do greedy right now. So what that means is it's going to output the best MLP out of all these epochs. It's going to actively update it. So let's look at where that is. So here's my train file. If you see, I auto-created this folder called training results. That happens automatically when you run this. And inside your training results is the greedy MLP, the best MLP at the moment. So as we train through more epochs, you see we're on epoch 2 right now. This will be updated whichever had the lowest validation RMSE, and appropriately the test predictions for that MLP with the lowest RMSE. Let's go ahead and stop this so we can look at this a little bit. So if we open up the CSV file, it's all the parameters of the MLP that the program needs to read it in. So we can read this in later for later predictions. It has all the weights, all that good stuff. The test predictions for that MLP are here. And again, this is actively being updated with whichever one had the lowest validation RMSE. And you can see here's all the spectra, and at the very end, we have the label, and next to it is the prediction. So you can see these are kind of close to me. They get pretty far. So if you remember, this is only on the first epoch, so the error has not converged yet. So some of these can jump around, but it's not too bad for one epoch, to be honest. Right, and then we also have validation results. And these are going to graph the epoch number, so since we only have one, there's only one row here, versus the total RMSE and the RMSE for each of your parameters. So you can track whatever you want. And I have the same thing for one for validation, one for training. So you can compare the learning curves. All right, that's it for training. So after you're done, you'll have a MLP that had the lowest validation RMSE through all the epochs done, along with test predictions on those. You can do whatever you want with those. Other output that you can do is you can output the exact predictions for every epoch for training, exact predictions for every validation, exact predictions for every test, and you can output the MLP after every epoch too. So instead of just having one, you'll have several folders here. Like you'll have one for epoch 1 and one for epoch 2, and inside this folder will be whatever you set to true here. So you can have the exact training predictions, the exact validation, the exact test, and the exact MLP, depending if you change these to true or not. All right, so the last thing I wanted to look at is how to test it. So say you have this MLP trained. Either you trained your own because you had new dimensions or you had new data, or you use one of the MLPs that we have trained presented in this paper, which are all in our GitHub MLP results, whichever noise you want. So the sample data I'm using is no noise. So I pulled this MLP here, MLP epoch 873, and that's what I have in this folder. So we're going to go ahead and read this MLP, and we're going to throw in the testing data and see how it does. So we're going to select test, full path to spectra, and it's going to ask for the path to the MLP after this reads. Yep, so enter CSV file, path to pre-trained MLP, no file extension. That's because it's forced to read it as a CSV file, because that way it reads and writes how it's supposed to. Minus the .csv, there we go. It's going to go ahead and read in the MLP. And it's going to read in all the pre-trained weights and bias, and if you see it shows the path it's written to. It's going to automatically write right next to where your CSV is. Since here's my test CSV, I have test results right above it. I'm going to open this up, and it's going to show all the spectra and all the predictions. So here's your test spectrum, here's all the albedo, and at the end we have what, like we showed earlier, we have the labels, and then next to those are the predicted values. And if you see, since this is a pre-trained MLP, these are a lot closer than that one we looked at before that only trained on one MLP. The values match up a lot more. These are all, Metallicity is pretty good. Here's all the log G. You know, they're not all perfect, and we looked at in the paper why there's some outliers that don't work. If you're interested, you can look at that in the discussion section. All right, I think that's it. So the code in general is written in C++, and we're giving you open source code so that you can really do whatever you want with it. It's pretty commented. Yeah, so best of luck. Like I said, if you ever have any problems, feel free to email. If you find any bugs, please email me. And this should work on both Mac and Windows. I've tested on both. But let me know if your OS, if you have an older version or something, it doesn't work, and I'll see what I can do. Thanks a lot.